Alright, this one's going to be about the wave function, because that's what we've been doing recently. And I think what's going to happen is I'm going to derive, in quotes, the wave function, like the way that Wikipedia does it. And I'm just going to try to go over that as carefully as I can, or as carefully as I want to. And yeah, just think about it, see where it takes me. What's my goal? My goal in doing this is to gain some perspective on what the wave function is, how I can think about it in a geometrical way. Because the world and that's the end of that sentence. All right. So I'm going to try to think super abstractly, or super to me, maybe not to somebody else, but super abstractly to me. And let's say that I have the okay, usually how it is in life, how it is that I know some things. So usually in life, there's some things that I know. And I'll draw those as dark dots. So every filled in dot is something that I know. Now, I don't know how I know it, but let's just say that without defining knowing something, it's just a feeling. I know it. So there's a lot of these things that I guess I know. Like I know that I know what a tree looks like. And I know what the class tree, I know if I see something, I know if it should be inside the class tree. I also know how to speak fairly well. I don't know how I know these things, but I do know them. And those are going to be these black dots. Okay, I'm just going to do a couple of them, but all right. Okay, let's just stop there for a second. So I'm representing. This is super abstract because this means no. I know it. I know it. Right? And then I'm putting this thing that I know onto a sheet of paper, and the question is, okay, so this is its own thing. The question is, where does it go on the sheet. So where does it go? What I mean by that is, what is the map from, where is the map? So for example, a possible map could be a timeline. So this is when I was born, and this is present. And so this is time. And so maybe there's a bunch of stuff, there's a bunch of stuff that I know from birth that's innate. This is innate. Innate, right? And then maybe at some time, I mean, this depends on how old you are, but at some time later, I know how to walk. Okay, that's walk. And then maybe here, how to talk. Walk and talk. Just one letter different. All right, and then ba 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 ba, and then sometime later, you might this might be like calculus. Okay, and then presently here, it might be something like tie your shoes. Okay, so you could map the things you know to a timeline on when you just knew them, when you realized that you knew that thing. And so then the distance between learning calculus and learning to tie your shoes, that delta t, is kind of the distance between, a measure of the distance between knowledge. Then it is a real distance because delta t is always greater than or equal to 0. And if we flipped the calculus and tie your shoes, we would still get the same distance, because the distance is the absolute value of event A minus event B. So delta t really is a metric, or a distance. All right, but that's not the only way. Like, for example, if we're doing something over here, this could be like, so the distance between knowledge points could be like, like which areas of the brain maybe light up, right? So if I have my brain, my brain is something like that. Maybe when I think about how to walk, this part of my brain lights up. And when I think about like how to talk, maybe this part of my brain lights up. So here, this would be the physical distance between the areas of the brain which light up. I mean, that might not be a good definition, because there might be a lot of overlap, and something like calculus might take up lots of different parts of your brain. So instead, maybe you want to think about it in terms of brain patterns. So if when I'm talking, I have a certain brain pattern, maybe the brain pattern looks like this. Or maybe a better way to draw a brain pattern is the way we usually see it. So maybe it's time and then signal strength, which I'll just call intensity. Maybe when I'm talking, my brain is doing something. I mean, this is not a really good measure either, because when I'm talking, yeah, no, so we need some sort of we need some kind of XYZ of the brain activity. So I put my brain, let's say, in the origin, and I measure the intensity as a function of in here. So I get some picture like this, and this represents all the areas of my brain that are firing during talking. And then I do the same thing, and then I do this for t equal delta t, and then all different snapshots, and then I get some sort of view of how, no, that's this, well, basically what I get, it's like an fMRI. I see how the brain activity changes over time, and I could compare that to different activities or different, no, this is bad, this is not good. Yeah, all this stuff with the brain, I think is, all right, so the question is, what is the distance between things that I know? If this is talk, I know how to talk. And this is walk. I know how to walk. How far away from each other are they? Maybe you could think about it like, what is the distance? You could think about it like, what is the minimum amount of brain that I need to talk? Okay, so that could be like, okay, so we could say that what is the minimum amount of brain power? Like if I start taking out sections of your brain, at which point do you stop talking? Similarly, if I start taking out sections of your brain, when do you stop walking? So the measure of the distance could be like the amount of brain you'd have to remove. The maximum amount of brain that you have to remove before, or in another way, the minimum amount of brain that you need in order to do that activity. So I'm guessing something like talking or walking, you probably need, okay, so let's do like, well, that should be a 0 there. So this should be a brain matter or brain amount. Okay, so for things like, so talking, walking, I'm guessing you're gonna need very small amount of brain. But something, and then, maybe like calculus, you might, uh, you might need a lot of brain power for that. So yeah, my guess is that in order to do calculus, you're probably using multiple areas of the brain. Blah 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 blah. Okay, but talking and walking or delocalized. But here, this is like localized function. So there's probably well-defined areas, I'm guessing, where talking and walking occur, whereas calculus is kind of more of a diffuse or more resource-hungry activity. So the distance you could measure by like the brain power. So the distance between talking and calculus is quite large. So that's more like a physical thing. I mean, another one that just came to mind is the um, because sometimes knowledge compounds. So, if you learn calculus, it makes it easier to learn differential geometry. So you would put the knowledge points of those two things closer together. Uh, and that would be like a correlation. So the distance could be inversely proportional to the correlation. So if something has a very high correlation, the distance is small. So usually um, like for example, going from walk to talk to why did I get stuck on doing this? I think let's just move on. Why? No ant. Okay. So let's just go back. I think the point is that it's if we want to define a distance between things that we know, that might require. I think it depends on what we want. What's the purpose of doing that, right? So let's just move forward. So we've thought about it a little bit, and now let's put that aside and move forward again. So I'm going to draw these things that I know again. And I'm going to assume that I'm ordering them in such a way where these distances make sense. So for example, this point, if I were to expand this point, if I were to blow it up, it might actually be a bunch of other points. But this point might be like some supergroup called math. So this knowledge point is all everything that I know about math, and within a small neighborhood around this point, we have everything strongly correlated to math. So the distance is small. Whereas over here, I might have like, oh, what's something that's different than math? I don't know. Yeah, it's difficult. Uh, Maybe this is like, it's just really hard to know. What's very uncorrelated to math? But, I mean, it seems like what do you know that's not correlated to math whatsoever? Okay, maybe like dance. Maybe this is like dancing, you know? But maybe there's like, but dancing, even dancing, you gotta predict patterns and shit. So it's very difficult. So let me just erase this. Okay, let me just say it this way. So these are groups. These are groups of things that I know, which, yeah, no, it's, see, I think I'm getting stuck with this definition here of uh, brain amount. Thinking too much in terms of the brain. I stop thinking about it in terms of brain activity and whatnot. Uh, okay, let's not think about it in terms of brain activity. Just think about it. So, for example, I know that calculus and algebra are separate subjects, and I know that dancing and math are separate subjects. So these are uh, distinct islands of knowledge, right? But integrals and derivatives are kind of related. So if this point was calculus, I would have integral and derivative kind of closer to each other within this supergroup. Okay, so like for example, I could have here could be like uh, pattern recognition, right? And then in here, I could have like math, and I could have like music and dancing. I don't know exactly if this is the correct way. And then within math, I could have like calculus and algebra and all these others. So calculus and algebra and the differential geometry. But they all kind of use pattern recognition. Just something, I guess it's something I know. If I see a pattern, I know it's a pattern. All right, so you can group things in an infinite number of ways, but so these just represent some super groups of knowledge. Okay, I think we're making a little bit of progress. And then, all right, so what I'm going to do now is I'm going to say there's also these open circles, and maybe these open circles can even be super close, but probably not, depending on what the how we define distance. Okay, so whatever. We don't know so let's just say these distances aren't representative of anything. This is just some super abstract way of thinking about knowledge. Okay? Remember these are known things. These are known things. Probably known is a better word than know it. And then this is unknown. These are things that are not discoverable. Or not discoverable yet. Okay, so I have something interesting here that I think I'm going towards. Okay. So there are okay, let's say that this is our perspective, right? Collectively, we know what we know. And collectively, we know what is unknown. Actually, I'm going to call this this is the known unknown. All right, and maybe I should do now. I regret making so many of these. So these are the hashed circles. Okay, these are the known unknown. I'll do the equivalent sign so you don't get confused with the dash. Okay, so what this means is that these, from our perspective, there's things that we know, and there's things that we know that we don't know. So this could be like dark matter, right? But this could be like matter. So we know what matter is, but we don't know what dark matter is. But we know that we don't know it. So it's a known unknown. And I'll also call this a K, and this will be a KU. Right? So now we can, we don't really use, we can just do circles. So, so if we take, yes. So if we take something which is known and we add it to something which is a known unknown, this is going to equal a known. Maybe that's a bad, maybe I should write it in this way. So if I have a known and I have a known unknown, right? And they kind of go to each other. What comes out are two knowns. Right? So maybe it's better to do like kind of like a chemical equation. So if I have one unknown plus one unknown, this goes to two knowns. Ugh. Yeah, just erase that whole thing. Okay. One thing is that it can't be any known and it can't be any unknown. Known unknown. it has to be ones that fit together. So this known has to have a piece, or actually it has to have a positive piece. It has to have some positive piece. Which fits in with this one, so that when they get put together, they an intermediary step, they form a big, so they form this big blob, and then here they begin to separate. Until you get okay. So you want to think about it in terms of like a chemical reaction thing, or some sort of like biological life cycle, mitosis or meiosis, whatever the heck it's called. This is how I'm imagining it. And then if you want to think about it in terms of like a mathematical sense, I mean, not that I'm had any of that fucking training, but if I take, let's say the things that I know are like my axioms. So I could have axiom 1, axiom 2, axiom 3, right? These are the things that I know. So these are my K's. And I could have a known unknown, which could be a 4, right? And then a proof would be 4 is equal to 1, say, plus 3. So then my knowns become 1, 2, 3, and 4. So this is so so I guess these two things fitting together. So if something you know sees something that you know that you don't know, but the thing that you know sees, oh, I can fit into that thing, it can convert it to something you know. All right. And then in the same way, let's say you know these three things, and you know that you don't know, like, you're like, you make a statement 4, and then you say, can I write that statement in terms of things that I know? If you can, then it now becomes something that you know as well. Okay, so I'm saying that this is what our perspective is that there's things that we know, whether it's self-evident, innate, or learned, we know them. And there's also things that we know that we don't know. There's a set, or you can also think of the KU as a set of questions that we have. So it's the set of all questions we can form. And this is the process of science, is taking what we know, reshaping it, and trying to fit it into the questions that we have so that we can turn it into two black blobs instead of one black blob. All right, and you can think of it in like a chemical reaction type of way or a biological virus protein sort of thing, or in terms of just proofs. Okay. Now, let's play this game with a different perspective. We are going to imagine that we have oh, yes, one more thing. Now, this is kind of interesting. Okay, so if we were to imagine this is some kind of game of life, how does it progress with time? So let's say that these things that we know are like little bugs or little ants, and these things that are known unknowns are like sleeper cells, and they're like zombies waiting to be awakened by the or whatever. And let's see what happens. So we would say at time, this is at t equals 0, and then t equal 1, and then so on. So maybe we know two things, and then there's three things that we don't know. Oh. So then maybe at this time, yeah, I don't know. Bahaha. Let's say that's what it is, and then okay, this is going to be a very naive first iteration. Okay, so in this stupid little example here, I'm imagining a certain dynamic situation where the end state is that we know everything from our perspective. So it could be that these are our axioms we start with. These are at t equals 0, we have these axioms. And then in the next time step, we use those two axioms to prove this question, and now it becomes something that we know. Okay? And then in the next time step, we use this thing that we've proved plus our axioms to prove these last two things. And then we have said here that all our known unknowns or Q's, that's supposed to be an S, have been answered. Okay, so there are no more questions. There's no more known unknowns. All right, but that's just one possibility. Like we could have. Let's start with the same initial state. So we have two axioms and we have three questions. And let's say that the same thing happens where we prove this question. But in proving this question, it actually raises another question. Okay, and then we prove these two things down here like we did last time. But each time we've proved these things, we get two more questions out of them. Okay, so in this case, by proving by proving, so that means that ku goes to k, we get more ku. So if I were to draw the equation, it would be like k plus ku goes to k plus ku, where these are some coefficients. Okay. So we could live in this type of universe. And I mean, that's why another way to visualize it is knowledge. Uh, let's think of all of our knowledge living inside of this sphere or circle. Okay, and this is Neil deGrasse Tyson's analogy. And then as our knowledge increases, we have all the things we don't know living on the surface. Okay, as our knowledge increases, so does the possible questions, right? So that would be an example of this type of universe that we live in. So the more that we absorb KUs, known unknowns, the more known unknowns we create. I mean, this is kind of just off the top of my head. It's kind of reminding me of like a almost like a feedback loop, or you know, what's I'm trying to think of a good simple example, like um, oh, if you got if you have dough, like sticky dough on your fingers, so both hands are like covered with dough, and then you're trying to get the dough off, but when you use the right hand to get the dough off the left hand, you might get a little bit off, but you just transfer the dough to the other hand. So when one hand ends up getting clean, but you get twice as much dough in the other hand, you know? I don't have a better example than that. Maybe I should. Or you can think about like designing like a piece of artwork. So maybe you've drawn like a circle and a square, and think, oh, that looks really good, and oh, maybe I need to add like a triangle. Like, okay, like all right, it's looking fine so far. And what if I added a star to it? Like, okay, it's good, and then a moon, and then it'd be like, no, I shouldn't have added that. Well, maybe I need to add like a squiggle here, and then okay, and then maybe this should be a three-dimensional thing, and so should this. And then, eventually you look at it like, oh, it's just a mess now. Whereas, like, if I would have stopped at a circle and a square, like that, this could say something, but this is just a mess. So at some point, I was adding to this, trying to make it better, but at some point it escaped. And actually, by me adding things to it, I actually took away from its artistic beauty. Now, this is uh, very artistically beautiful, and this is just somewhat. All right. If you can't tell, if you can't tell by now, I am super fucking bored. Okay. So let's. Okay, so the question is. The question is, that we're left with is so at the end, when time is equal to end, shout out to MATLAB, does the knowledge look like this? Do we know everything? Do we know everything? So, I mean, and there's the thing, right? There's to some sort of sufficient end, right? Like the word sufficient matters because I know how to tie my shoe, but I don't know how I'm able to tie my shoe. But I almost don't. It's almost sufficient just to know how to tie my shoe, because I don't. I'm not too interested in knowing exactly how that happens. But I mean, knowing exactly how it happens is related to um, how I can know anything, or maybe like how the brain works, and maybe at a final state of the universe, we would as collectively want to know how the brain works. So or for example, this is intelligence, AI, like whatever. We want to know. If we had a final state where we didn't know what intelligence was, then that wouldn't make people very happy. So this is kind of subjective, right? Because there could be another final state where we have a circle here. We draw a circle around everything that we know. And then we say, okay, there's some things out here. And we say, yeah, but we don't care about these things. These things are like, uh, okay, well, here's a question. If we had a, okay, if one of these points is a grand unified theory, then are there known unknowns? If we had a physical theory for everything, can there be known unknowns? In physics, no, right? So anything that could be framed in terms of physics would be knowable if we had a grand unified theory. So the question is every question founded in physics? So is every Q in physics? Physics. Why is the sky blue? How does the brain work? What is dark matter? What is intelligence? What is at the center of a black hole? What if we went through a wormhole? Can everything be tied back to physics? Well, what about things like, okay, so let's say that intelligence intelligence is just physics in the end. Okay. Okay, I think I've pressed this point enough. Let's move forward for a second. Okay, so I'm trying to. Let's assume that we get to a point like this here, where we from our perspective, we know everything. We have grand unified theory of physics. We have AI. But if we have AI, we know. Do we know how the AI works? Do we even know that it's AI? All right, for the sake of moving forward, let's assume that we can get to a state like this, or in a state which is approximately this. So maybe there's still a couple of KUs out there, floating out there somewhere, but for the most part, we've got things nailed down. Okay, there's no there's not huge problems like what are emotions, what is intelligence, what is the soul, what is consciousness, what is dark matter, what's dark energy. Like these are huge holes looming in our knowledge. Let's assume we can kind of wrap this up to some point, and I mean, maybe we can never do that though. Maybe the more we answer, the larger our sphere of ignorance grows. Maybe we have a negative feedback loop sort of thing happening here where as we start to kind of draw our picture, as the more it looks like it's making sense, actually, the more it's not making any sense. You know, maybe it's like this is time in the universe, and then this is confidence. This is confidence. You know, confidence in case. You know, then I don't know if I should draw a sine or cosine, but let's draw a sine. You know, it might look something like this. Or it could be, you know, so you could have these peaks and valleys of your confidence in your theories. Uh, okay, but let's just take just some time. And we're going to have our knowns. We'll have our known unknowns floating around out there. Okay. And this is, I wrote our perspective, and this would be someone looking at you. So for somebody observing you, they think, okay, this person knows this, they know this, they know this, they know this. You know, they clearly they know how to talk, they know how to walk, they know how to tie their shoes, they know how to do calculus, they know how to do physics, they know how to cook, you know. But I know that they don't know. I know that they don't know how to do this, this, and this. Now, let's say I can read somebody's mind. Okay, so I can accurately reproduce this map of all the things that this person that I'm looking at knows and knows they don't know. Okay, now I will also find these open squares. And these open squares are things which unknown unknowns. They're unknown unknowns, or UUs. Okay, so these are things that I know that this person doesn't even know that they don't know it. Okay, so you could think of this as like this person could be like a god. God's perspective. The God perspective. Okay, so God looks at us and says, this is what they know, this is what they know they don't know, and this is what I know that they will never know. Or this is an unknown unknown to them. They don't know that they don't know this. So, I mean, we are unable to even come up with an example. I cannot even give you an example of an unknown unknown. Because I can only know I can't see past the questions I have not yet asked. To quote the Matrix, I can't see past the questions that I have not asked. So these are questions that I haven't even asked. That's a good cues I have not. I don't know why my pen is not working right now. Okay. Where's my mouse? So, for example, like grand unified theory would be one of these known unknowns. But I don't even have I can't have an example. Because as soon as, interesting. So in this case, as soon as I have a known unknown, that is an interesting question. So a unknown unknown, how does it become a known unknown? Very, very interesting. Once it's a known unknown, then I know how to turn it into this is a proof. Okay? So once it becomes a known unknown, I have the machinery. I have lots of machinery to turn a known unknown into a known. But if there's something that I don't, I unknow that I unknow it, how does it become a known unknown? So how does a UU go to a KU? That to me that's very that's a very interesting thing to think about. So one option is this could be like experiments. Experimental, so a new experimental observation. And then here by theory. So we have a new experimental observation, which basically takes something that we didn't know, turns it into something that we now know that we don't know. And then a theory takes it from something we know that we don't know to something that we do know. All right, so another way is that a theory, as a concept, a theory could produce a known unknown. So you could have this sea of unknown unknowns, and you could have an experiment which okay, so this is what I've already described. So I have a known unknown which goes to the is observed by an experiment which spits out a known unknown, which then goes into the theory, which comes out as something which is known. Now, the theory this is the C of UU. Now, the theory goes through, the theory creates a prediction prediction is a possible world. But an experimental observation, if I do an experiment, what am I doing? I'm taking something that I know. So an experiment, taking something that I know and I'm adding it to something else that I know. And that's giving me a known unknown. So if I look in terms of the proofs, I could say for uh, I could do it both ways. Right? I could say 4 is a result of adding things that I know 1 and 3, or I could say 4 leads me to find that 1 and 3 are needed to construct it. So I can either take something that I know that I don't know and drop it back into stuff that I know, or I can take 2 things that I know and I can add them together to find something that I don't know. For example, before we knew quantum mechanics, we took light, which we thought we knew, and we shone the light onto a piece of metal, which we thought we knew, and we discovered something that we didn't know. So I guess that when we take something that we know let's take this. We take 2 things that we know. We know light and we know metal. And we discover some known unknown. Well, we can always add. It's like adding 0, I guess. It's like adding something that you don't even notice it's there. That's the right way. So then I'm just trying stuff out. I don't know if this is correct or not, but okay. So if I take my light and metal and I look at my new phenomenon, So this is the photoelectric effect. And this would be like Newton's photoelectric effect. This would be like Newton's laws. Newton's laws. Yeah, so if I take the photoelectric effect and I apply Newton's laws, then whatever the difference is, so this is like the theory, if I take the experiment and I subtract it from the theory, whatever the difference is, right? So my unknown is going to be equal to the known unknown minus the known. Something like that. So we don't directly. So this is the hard part, right? That the sea of unknown unknowns. We don't know if it's actually there because we can't just pull it out. We have to add or rearrange the laws and the stuff that our knowledge we currently have, and subtract that from known unknowns, and whatever's left over is a hint of this unknown unknowns. So this is like the difference between experiment minus theory. Curve fitting. Right, so if I have some data, okay, and my theory looks like that, then everything past this point, these are unknowns. This is an unknown unknown. So what I have to do is take the difference here so now this could be like the quantum mechanics. Quantum mechanics was a known unknown, which you can it be ultraviolet catastrophe. That was a known unknown. Okay. So the message here is keep searching for UUs. And one way by experiment, and two by formally constructing possible, actually logically, worlds. Okay, and compare them to experiment. So experiment, so for example, this is the real world, right? As discovered by every possible experiment. Every possible experiment has discovered the real world, whether that's the experiment of opening your eyes up, or measuring the charge of an electron, or firing electrons at a piece of tinfoil. This is the real world as given to us by experiment. Experiment goes to the real world. So, okay, here is a possible world, logically possible world. Logically possible means, I guess I'm going to say consistent. So this is given to us by theory. So you can construct a theory, a sound theory that's logically consistent, and it gives you a possible world. Like for example, Euclidean. I mean, I don't know enough to say that, but like probably this whole thing has been, I don't know how to say it, but so you come up with axioms, set of axioms, and some dynamical rule, and you say, okay, so this possible world has this set of things in it. And I know in the real world I have this set of things. And then I say, okay, this thing maps to this thing. This thing maps to this thing. This thing maps to this thing, okay? And if I'm able to attach a thing from my possible world to everything in the real world, okay, then this is a pretty good world. But let's say there's a subset of stuff which does not map. So does not map. Then where does it go? Right? Does that mean that it goes to somewhere out here? And then my real world has to bubble out to include it? Or does that mean that this whole possible world is no more? It's not a good theory. So it should be that if I create, these are my logical possible worlds, and this is overlap with the real world. And let's say that world 1, 2, 3, and also we need to keep track of the leftover, right? So if the first one overlaps, say 70%, okay, but there's leftover, say there's 50% leftover. Here overlaps 90%, and there's 19% leftover. And here overlaps 99.9%, and there's say 1% left over. Okay, then let's say that this world, right, it overlaps. So this model, this logically possible world, gives us 99.9% accuracy, except it predicts 1% of stuff that we haven't seen. Okay, which means that these are our unknown unknowns, and so that we can study them in the model and expand. So let's say yeah. So we're doing some kind of fitting between sets. Now the problem is overfitting, right? Because I could have the case where I have there's 100% overlap. It's perfectly fit, and there's nothing left over. This is overfitting. So what this means is that I'm really, really good at predicting the real world, but because there's 100% overlap and there's nothing left over. But it's not so good because I haven't found any unknown unknowns. So either that means that there are no unknown unknowns, so there's no unknown unknowns, or it means that I've just predicted the world. I haven't discovered anything new. So for example, let's say we create a model of the this let's say Dirac. So Dirac, his Dirac equation. It explained a lot of things really, really well. But there was this leftover bit. There's this solution to his equation where you could get like negative energies. And I think, now I probably shouldn't say this because I don't really know. But the antimatter stuff. So he said, oh, well, it's this new particle. And everyone said, no, it can't be right because there's no antimatter. And so even though it agreed with the experiment, I guess, because it had this theoretical consequence that didn't seem physically to line up with the real world, then it was thought that it should be thrown away. But it turned out that antimatter was just an unknown unknown. So that's a perfect example of how a theory can construct a logically possible world and where that possible world does not overlap with the real world, well, now you've just turned an unknown unknown into a known unknown. Perfect. Awesome. Okay, the shit is making sense. Okay. I just realized that this says P. I'm such a fucking idiot. Okay. All right. What to do now? Okay, so the point is that point. So the point is that we have ways. Fucking Christ. We have ways of finding UUs. Okay, so you have two ways of finding UUs, either by experiments or just increasing by experiment, which I mean is just taking things that I know and putting them together and seeing if something comes out that doesn't fit with the theory. And the other one is by using theory to construct logically possible worlds and then mapping that model to the real world of stuff we do know and seeing if there's anything left over. So we have ways of finding unknowns, but do we know? But we don't. But we don't know. That might come back to haunt me. We don't know if we don't know when to stop the halting problem. Okay, but so we're running this program to find unknown turning the program. We are a program runs. The program runs and it turns unknown unknowns to known unknowns. There's no stop clause. There's no Santa Claus and there's no stop clause. Okay, so in that we are like a program. And now I am really outside of my comfort zone here because I don't know what the halting problem is. I'm not a computer scientist. But I think that it is. No, I don't know. I don't know what the halting problem is. I know I read it in a book once, and I've forgotten it. I should read that book again. Dude, let's just search it. Okay. Probably gonna have to make a part 2 to this video because we're nowhere near the wave function. Or maybe we are. Halting problem. In computability theory, the halting problem is the problem of determining from a description of an arbitrary computer program and an input whether the program will finish or continue. Okay. All right. So, okay. Don't know. Halting machine. Okay. Input string. What the fuck? Halt, no halt. This allows. Oh my god. Input. Okay. Input string. Halting machine. Yes. Halting machine halts on input W. No. Halting machine does not halt on input W. Okay, so this halting machine. So how do we relate it to us here? So let's say that the input would be like I have. So the program is turning UU into KU. So it says, do while one, while some condition has not been met, try experiment. Okay. Uh, have you found a UU? Has UU gone to KU? If not, then try 2. Okay. Does UU go to KU? Okay, no. Okay, try another experiment. Try another theory. Maybe that's the program. And then eventually the program turns a UU into KU, and then it keeps going. Okay, maybe I don't know. But then, let's say that our program has ran for so many times and it has turned 5 UUs into KUs. So by inference, it's that, well, we must have found, there are at least 5 UUs out there in the sea, but we've taken them away. So how many more are there left are there? So the question is, how many more UUs are left? How many UUs are left? So it would be, if I run this program, if I input the codes to run this program, if I start running this program, will I find another U? Yes or no? That can't be answered. So we may not actually know if we're done. There's always going to be UUs hanging out there in the sea of UU. It seems. So it seems. Oh my god. Okay. What if Hilbert space is kind of like connected or by, or I don't, do you use the word isomorphic? I don't fucking know. Knowing space. So the kind of this stuff we've been talking about so far is like kind of like knowing space. And is that connected to Hilbert space? Yeah. Okay, and is there a connection between Hilbert space and real space? Well, real space, I'm going to say that's not a question. Hilbert space. Right, so real space is like the distance between x and y. Hilbert space is like the inner product between these vectors. And knowing space is, you know, like u goes to ku goes to k, or so are these related somehow? So if this is my Hilbert space, um, hmm. I can divide my Hilbert space into like two things. So this is what we would call the environment normally, and this is the system. So the system is going to be the set of all my knowns. These are the states of a system that I know, like spin up, spin down, or things. And the environments are the known unknowns. So I don't necessarily know the state of the environment. Like if the environment is a heat bath, sometimes it's called, which is a soup, a hot soup of electrons or whatever. It's an N, fuck. I don't necessarily know. Are they known unknowns or are they knowns? Or maybe the state is too complicated. Couldn't it just be like a thermal state? Okay, let me just go forward with the analogy. So let's say that the environment, you know the environment's there. Like you can ask questions like, what is the state of the environment? What is the interaction? What's the interaction between the environment and the system? So these are all questions. Just to talk about it on an abstract level, these are all questions that we know how to ask. So my total Hilbert space would be like this system of things that we know. So presumably I know all the different possible. I can write down the states of my system. But what I know to be unknown is the state of the environment or the interaction with the environment in the system. Something like that. Or it might be that I know this might be misleading. I mean, maybe not. That might have been okay, actually. Mm-hmm. But I think, yeah, I think my Hilbert space, like my Hilbert space, so my Hilbert space will be written as stuff that I know, tensor product of stuff that I know that I don't know. I'm going to try this out. Let's see if this is wrong. Oh. Or I'll say that this is HK. All right. So then HK and HK is normally written as H of the system, H of the environment. Or this will give you the H of the system plus H of the environment plus the interaction. So if I know what these states are, so if I know the states for the whole system and environment, then H, U, and I'll say they're labeled K. That's a K. Which, I mean, this is all bullshit. I mean, it just doesn't really mean anything. I don't really know what I'm doing. I'm just thinking. But all right, I think I've done enough bullshit. So yep, I've just been thinking, and I've just been thinking. So I'll probably end it here because I'm tired.